There's a little thing I want to show you. It's a puzzle, and it has bothered me for a long time. Because the answer is not where you think it is. Stick a little pair of headphones over your ears. The noise-canceling kind. You're sitting in an airplane. Engines are roaring. A baby is crying. You press a button, and the world goes quiet. Just like that. The roar is gone. The crying fades to nothing. You can hear your own heartbeat. Now take that same idea and try it with light. Stand in a sunlit room. Pull out a flashlight. Shine it at the wall. The wall gets brighter, right? More light, more brightness. Always. So I ask you this. Can you build a flashlight that shines on the wall and the wall gets darker? Same wall, same room, same eyes, but you flip the switch and the wall is dimmer than it was before. Not blocked, not shaded, actually dimmer, because of the light you added. You can't do it. Nobody can. You can buy noise-canceling headphones for $50 at any drugstore. But there is no flashlight anywhere on Earth that cancels light from another flashlight. Not in your house. Not in a research lab. Not in any laboratory I've ever heard of. And the thing that drives me crazy is this. Sound and light are the same kind of phenomenon. They are both waves. The math that describes them is, in many ways, the same math. The principle that lets you cancel sound is a principle that on paper ought to let you cancel light. So why does it work for one and not the other? I want to figure this out with you. Let's get into it. We have a puzzle. Two waves. Same principle. One cooperates with us. The other refuses. What's different? Let me lay out what we know. Both sound and light are waves. That word wave sometimes confuses people because they picture water, splashing, foam, the ocean. But a wave, in physics, is just a pattern that travels. A disturbance that moves through something, or in the case of light, through nothing at all. The pattern goes up and down, and the up and down has a length. We call that the wavelength. And it has a rate of vibrating. We call that the frequency. Sound is a wave of pressure in air. The air molecules get pushed together a little, then pulled apart a little, then pushed together again. That pressure pattern moves outward from whatever made the noise, and when it hits your eardrum, the eardrum jiggles in sympathy with it, and your brain hears it. Light is a wave of something else. It's a wave of electric and magnetic fields, oscillating together, sweeping through space at a speed nothing else can match. It hits the back of your eye, jiggles certain molecules in there, and your brain sees it. Different stuff doing the waving. But the same basic idea, a pattern moving through space, up and down, with a wavelength and a frequency. And here is the part that matters. Both of these waves obey a principle so old that we knew about it before we knew what waves really were. It's called superposition. Big word. Simple idea. Superposition just means this. If you have two waves moving through the same place at the same time, the total wave at any spot is whatever you get by adding them up. Add a wave that goes up to a wave that goes down, and they cancel. Up plus down equals flat. That's the trick that makes noise-canceling headphones work. The headphones have a little microphone listening to the outside. They measure the wave coming in. They compute the exact opposite wave. And then they play that opposite wave into your ear at the same moment the original noise arrives. Up plus down. The waves cancel. Silence. Beautiful. Elegant. So why does it not work for light? I have to be careful here, because the obvious answers are all wrong. Let me walk through them, and we'll see which ones survive. First obvious answer. Maybe light isn't really a wave. Maybe it's just particles. And you can't cancel particles, you can only block them. That's wrong. Light is a wave. We've known this for over 200 years, since a clever fellow named Thomas Young set up a little experiment with two slits cut into a piece of paper. He let light shine through both slits and land on a screen. And what showed up on the screen wasn't a bright spot. It was stripes. Bright, dark, bright, dark, bright. Light plus light, in certain places, made darkness. That's interference. That's wave behavior, plain as day. So light, whatever else it may be, is also a wave. And it cancels itself, in the right setup. Cross off that answer. Second obvious answer. Maybe sound and light are just fundamentally different kinds of things. Sound is mechanical. You need air, or water, or some material to carry it. Light is electromagnetic. It can travel through vacuum. So maybe the cancellation rules don't apply across the board. This one is closer to a real answer, but it's also wrong as a complete explanation. Both sound and light obey superposition. Both interfere. Both can cancel, in principle. The fact that one wave is squeezing air and the other is wiggling electric fields doesn't change the math. The math says opposite waves cancel. Period. Cross off that answer too. Third obvious answer. Maybe it's just hard, and one day we'll figure it out. Just give it time. This is the most tempting wrong answer, because it sounds humble. But it's still wrong. The reason you can't cancel ordinary light isn't an engineering problem we'll crack next Tuesday. It's a problem that runs into the actual numbers of nature. And once we look at the numbers, you'll see why no amount of cleverness will get you there with the same trick we use for sound. So we've thrown out the easy answers. Let's start hunting for the real one. The first real clue is speed. Sound moves slowly. By physics standards, embarrassingly slowly. About 340 meters per second through air. That's roughly the speed of a fast bullet. You can outrun sound if you've got a jet plane. You can see a flash of lightning, count the seconds, and figure out how far away the lightning is, because the thunder takes a noticeable amount of time to reach you. Light moves fast. Absurdly fast. About 300 million meters per second. 1,000,000 times faster than sound. In the time it takes sound to cross your kitchen, light has bounced from here to the moon and back. Several times. And this matters enormously. To cancel a wave, you have to do three things. In order, you have to detect the wave coming in. You have to figure out what its opposite is. And you have to emit that opposite wave, so it arrives at the right place at the right moment. For sound, you've got time. Not a lot, but enough. Sound travels a few meters in the time a fast microchip takes to do its calculations. A few milliseconds is an eternity for modern electronics. The headphones grab the wave, flip it, send it out, and it arrives at your ear right when it needs to. The whole operation has time to breathe. For light, you've got no time at all. None. By the time a sensor noticed a wave of light, computed its opposite, and tried to emit the canceling wave, the original light has already gone past. Already hit your eye. Already bounced off the wall and is on its way somewhere else. Light moves through the width of your eyeball in something like 1/10 of a billionth of a second. You're not catching that wave with any electronics we know how to build. The race is over before you've heard the starting gun. That's clue number one. Speed. A big clue, but it's not the whole story, because in principle you could imagine very, very fast electronics. And maybe one day the speed problem could be tackled. So let's look at the second clue. Frequency. A wave has a frequency, which is how many times per second it goes up and down. Sound waves you can hear have frequencies between about 20 cycles per second on the low end and 20,000 cycles per second on the high end. The deepest rumble of thunder is a few cycles per second. A piercing whistle is several thousand. The whole range of human hearing fits inside the range from 20 to 20,000. Light has frequencies starting around 400 trillion cycles per second for red light, and going up to about 750 trillion for violet. Trillion. With a T. Put it differently. The highest sound your ears can hear vibrates 20,000 times a second. The lowest light you can see vibrates 400 trillion times a second. The ratio between the highest sound and the lowest visible light is roughly 20 billion to 1. To cancel a wave, your equipment has to operate at the wave's frequency. To cancel a sound that vibrates 20,000 times a second, your speakers have to vibrate 20,000 times a second. Speakers do that all day. To cancel light, your equipment has to oscillate at hundreds of trillions of times a second. Our best electronics, the fastest microchips ever built, operate in the range of a few billion cycles per second. We're off by a factor of about 100,000. We are not close. We are not in the same neighborhood as close. We are not in the same country as close. That's clue number 2. Frequency. Our machinery cannot keep up. The third clue is wavelength. A sound wave you can hear has a wavelength between about a centimeter and 17 meters. A meter is roughly the height of a child. So sound waves are big. They are chunky. They have features on the scale of furniture, of rooms, of buildings. A light wave has a wavelength between about 400 and 700 nanometers. A nanometer is a billionth of a meter. So a light wave is about 1/10,000th the size of the period at the end of a sentence in a book. Why does this matter? Because to cancel a wave, you have to know exactly where it is. You have to put your opposite wave at the right place, lined up with the original peak to trough, with precision smaller than the wavelength itself. For sound, that precision is, say, half a centimeter. We can do that. We can build a speaker that puts a sound wave in the right place to within half a centimeter, no problem at all. For light, that precision is half of 400 nanometers, which is 200 nanometers. 200 nanometers is about 1,000 times smaller than the thickness of a human hair. To cancel a wave of light coming at your eye, you'd need a device that knows where it is, what it's doing, and where to put the cancellation, to within a fraction of the size of a virus. 3 clues. Speed, 1,000,000 times faster. Frequency, 100,000 times higher than our electronics can handle. Wavelength, 10 million times finer than what we can manipulate with ordinary devices. There's a 4th piece to this puzzle, and I think it's the prettiest one of all. It's about how messy light actually is. Imagine the sound in your ear right now. Maybe a hum from a refrigerator. Maybe the rustle of leaves outside. Maybe somebody talking in the next room. Each of those sounds has a source. Mostly one source. The refrigerator motor is one motor. The leaves are rustling in one wind. The voice next door belongs to one person. Each source produces a wave that has some pattern to it, some rhythm. It is not random. It has features your ear and your circuits can track. Now think about the light hitting your eye. It came from the sun. The sun is a ball of glowing gas, and every atom in that gas is independently emitting light. Trillions upon trillions of atoms, each one releasing a tiny burst of waves, each burst lasting only a few nanoseconds, each one with its own random phase, its own random direction, its own random color. By the time all of those tiny bursts have traveled 90 million miles and reached your eye, what you have is not a wave. It's a storm, a blizzard, a complete chaos of overlapping, crisscrossing, uncorrelated wavelets arriving from 1,000 directions with 1,000 colors at 1,000 different times. To cancel sound, you have to cancel a wave. To cancel light from the sun, you have to cancel a hurricane of independent wavelets, every single one of which is doing its own thing. You can cancel a single wave. We cancel sound because sound, even messy sound, is structured enough to track. But the ambient light in your room, the kind that lights up your face and your morning coffee, is so chaotic that even if you could match its speed and its frequency and its wavelength, you'd be trying to predict the unpredictable. Each little burst of light from each little atom on the sun is its own random gift. You can't see it coming. You can't prepare for it. By the time you've noticed one burst, 10 million more have already gone past. So now we have 4 clues: speed, frequency, wavelength, and chaos. Stack these 4 facts on top of each other, and you don't get a difficult problem. You get an impossible one. Not impossible in principle. Impossible in practice. Impossible by a margin so large that no engineering improvement, no faster chip, no smaller sensor will ever close it. The gap is not a step. It's a chasm. All right. So that's the end of the story. Light just can't be canceled. Wait. Wait, wait, wait. Because here's the part of this puzzle I love most. Light can be cancelled. We do it every day. It just doesn't look anything like noise-canceling headphones. Pick up a pair of eyeglasses with a coating on them. Hold them up to a window. The lenses look almost invisible, don't they? No glare. No reflection. That's not because the glass doesn't reflect. Glass reflects light. Always has. The reflection has been cancelled by a thin coating on the lens. The coating is a single, precise layer of material, about 100 nanometers thick, painted on the surface. And when light hits it, some of the light bounces off the top of the coating, and some of the light bounces off the bottom of the coating. Those two reflections are slightly out of step with each other by exactly half a wavelength, and they cancel. Up plus down. Silence, but for light. Look at a soap bubble. The colors swirling on its surface. The swirling rainbow patterns, those are interference patterns. Some wavelengths are canceling themselves. Some are reinforcing themselves. The bubble is doing exactly the same trick as your noise-canceling headphones, but with light, in real time. With no electronics, no microphone, no battery. Just a film of soapy water doing physics. Look at the oily sheen on a puddle of water in a parking lot. Same thing. Light canceling light. So why does this work when our headphone trick fails so badly? Because the cancellation isn't being done by a sensor and a speaker. It's being done by geometry, by the shape and thickness of the material itself. The thin coating doesn't need to be fast, because it's not reacting to the light. It's just sitting there, and the light interferes with itself as it passes through, naturally, automatically, every time. The coating doesn't ask the light, what frequency are you? It doesn't compute an opposite. It just sits there at exactly the thickness that makes a certain color of light cancel when it bounces around inside. Passive. Permanent. No electronics needed. This is the deeper answer to our mystery. Light can be cancelled, but only by structures that are themselves shaped on the same scale as the light. Things a few hundred nanometers thick. Things sized to light's own wavelength, or smaller. We can cancel light with matter. When the matter is built at light's own scale, we cannot cancel light with sensors and speakers, because sensors and speakers are built at our scale, and our scale is gigantic compared to light's wavelength. For sound, the world is the other way around. Sound's wavelength is on our scale. The size of a sound wave is the size of a room, a chair, a person. Our hands and our machines and our speakers are perfectly matched to sound. We are the right size to bully sound around. Light is built on a scale we don't naturally inhabit. To play games with light, the way we play games with sound, we have to descend into the world of the very small. Nanoscale coatings, diffraction gratings, photonic crystals. There are people who do this for a living, and they do beautiful work, and what they produce looks like magic. But it isn't noise cancelling. It's something stranger and more permanent. It's cancellation baked into the material itself, frozen into the geometry. I want to leave you with one last twist, because I think it's the most important thing about this whole puzzle.